Okay, guys, let's continue. All right. So after you have triggered this buffer overflow, already you notice that you can take control of the instruction pointer, meaning you can take control of the flow of the program, right? So because this is a stack-based overflow, what it happens here is that you are saving your back pointer into the stack after something happened on the application, after calling a call function. If you want to know exactly what, you have to reverse the app. That's why the breakpoints are useful, because then you can go back and reverse the app and see what is the offending part of the code that is actually triggering this. We already know where. It's through the language for menus and this action, this value inside it after it's having moved into memory and going from the being saved into the stack, and then from the stack you are taking the back pointer and the rest, and because you are overflowing the rest of the values in that were already stored in the stack, you are overflowing everything, and there was no protection for that in this binary. Then this happened, right? So, but we want to know exactly how many A's or how much junk do we need to send into the stack if we want to take control of EBX, EIP, or the structure exception handlers. So how do we do that? So for that, we can use this ECR or Mona, of course, but we're going to use ECR. So let's do that. And here I have the commands, so I can share those with you later. So ERC, so no ECR, ERC. So here inside commands, the first thing that we want to do is to set the working directory. I'm gonna set it to training directory. You have to change it for your own. Let me also paste it on the chat. So you set the config, set working directory, see users, your path, and then click OK. And you will see no output here. If you want to see the output, you have to go into the log tab. So click on there. And then you will see here the output from the ERC plugin. If you are not seeing anything, it means that the plugin is not loaded. So it doesn't, if it doesn't say plugin ERC XDBG, or you can actually check it by going into plugins, and then by default, as I mentioned, you have a Scylla plugin. But if you don't have ERC XDBG here, then it means that it's not loaded, right? I already explained it. If you have any issues with that, please let me know. But I already explained that how to load it into there. So ERC, remember, go into the log tab, and then here you can type, if you don't know the commands, you can type ERC to call the script, and then -help, and it will give you the help window. That is the same help that we seen at the beginning of the training into the GitHub page. But here, what is now interesting for us is the creation of a string that we can follow along in order to find what's the offsets that we need to use for overriding the IP. EBX was overridden as well, or the SEs. So to create a string, we can use a pattern command that basically is going to create a pattern. It's a cyclic type of pattern, and as says here, this acyclic type of pattern that generates a non-repeating pattern. You can also create this pattern using exploit pack, but you already have it here on this plugin, and then you can, as it says here, a pattern of pure ASCII characters can be generated up to 20,277 and up to 69,923. If special characters are used, we are gonna choose the regular ones, and we're gonna create around 3,000, 4,000 just to be sure. The offset of a particular string can be found inside the pattern by providing a search string must be at least 3 characters long. So this is what we're gonna use. So create a pattern. It's gonna be ERC pattern, and then the length. I mean, how long it should be. So it's gonna be like this. And if you want to set the, well, that's your name. And this is for the pattern. Let me copy choose everything here, so you already have it. And I don't have to copy one by one. So this is the command that we're gonna use. And if you have set the config of this working directory first, then the pattern is gonna be created not only here, but also in your desktop, in your folder. Okay. So here you see it created this pattern file. What I have it in ASCII. This is the pattern, or in hexadecimal. It's a non-repeating pattern. So what it means is that if I look for a capital A, lowercase, it will not be repeated here. So if I look for example, for this, right? So I will not repeat it. So what's happened is that after, if I overwrite something in memory, and let's say I overread it in memory using CA2, CA3C, CA, for example, then because it's a cyclic pattern and I know exactly that this is 1 byte, this is 1 byte, this is 1 byte, this is 1 byte, or the length of it, so it's 1, 2, 3, 4 to 3,000 until 3,000. Then I can use a script to say, hey, I have overwritten this, then give me the length between the start and this, right? If I look for it, you will find it here. And then the script is going to be, well, intelligent enough to tell me from 0 until here, what is the length. And then that length is, we will use that as an offset. So then for us, it will mean that from here until here, we have to send stuff. Then after that, it will come our values that we want to override. So how do we do that? Because now we need to send, we can send manually. So we can send manually this and then paste it inside here, inside the language for menus and messages. Or well, this is for the POC, for creating the POC. So we are creating, well, let's do it, let's do everything with Python. So it's it will make more sense. So let's introduce this. First, we're gonna create a file. It's gonna be called crash.txt. That's something I prepared pre-order the training. So let's restart the program, run it. Continue execution until the program is running after the breakpoints. I'm gonna go into edit, GUI here, and then first I'm gonna run this one. This file is gonna create crash.txt. Then it's gonna write 41, that is the hexadecimal representation of the capital letter A by 3000. It's gonna write that into buff, and then it's gonna write that into the file, close the file, and then the file is gonna contain the A's. So let's just try it. POC, going to crash, then we have it here. But we already done that manually, so we're gonna jump into the next part of it, that is running the crash and then adding the pattern, right? So here we have created 3000 A's, 3000 a pattern of 3000 length. That is the same one here, as you can see, because it's see, it ends up with the same because it's just because of the length. We can add this as for you for future reference, because later I will share the scripts. And then we're gonna save it inside the crash file. So let's run it. Double click on it. It just run, and then if we go into this file, then we have the pattern in a string. I'm gonna copy the string, and then we put it here inside, trigger the exploit, press OK. And now if we go into the GUI itself, we see that on the stack, here in the memory, ESP points to the stack. And then the instruction pointer has been overridden with our values. And that's our pattern. So now if we go into log and we use the command find NRP. The find NRP is going to generate a table detailing whatever a repeated pattern has been found in memory. So basically, it's going to look into memory, and it's going to try to find the memory space. It's gonna try to find our pattern in memory space. And then if a register or any seed has been found in that memory by the pattern, then it's gonna tell us, okay, from 0 to the offset of that pattern. So basically, it's gonna say, hey, I found in memory this. I found in memory this. Then it means that from 0 until here, then that's the offset. So let's say 1000. So from if EBX, let's say we remember we knew already that EBX was going to be overridden. So here we have EBX. So it's 41, 36, C, 6A, 41. So let's look for that. So it's 41. I mean, I'm doing it manually, so you can see how it works. So, because it's going to be the hexadecimal representation of it. It's going to be for a. Well, I need to change this to hexa. Any case, you got it. You get it right. So it's the hexadecimal representation in ASCII of where it belongs, and then from 0 until there, then it's going to tell us the length. Let's do that. I mean, there's no point into doing it manually. So let's call ERC minus find NRP, and do I have the command there as well? Yes. So we call that, and now it's gonna take 1 minute or so. Depends on how big is the memory assign it this thread, then it's going to look for that. And as you can see here, and it should have also, yeah, created the log file into your working directory if you have set it up previously. And then it says the process name, air GUI.exe, final PTL generate the blood at this time date. Then it finds that ESE points to into the particular position 0 for amounts of bytes and so on, and ESP at position 297. EIP is overridden with pattern position 292, and so on. And then we also know that we're going to use later on that SEH register has been overridden in the position 1012. But remember, first we're going to do the stack-based overflow. All right, so if it's a stack-based vanilla type of a stack-based overflow, it means that we are going to take control directly of the instruction pointer. Then we need to overridden this by 290. So let's do that. So if we want to take control of that, let's make that so we say 292. It might be different in your environment, so this it as well. 292. And then we're gonna let's also copy this one and not save it. So let's do it here. And then we're gonna name it vanilla stack based. All right. So what do we need here? So we need first we need to send junk 292, and then something that we can put there. So we're gonna put ABCD in reverse because the Indianness. Then rerun it. And let's see if we can take control of the instruction pointer on this vanilla exploit. So we need to run it, crash, and then you see we have 292 A's plus DCBA. And then we go, after it's running, we go into here, edit, GUI, paste it here. Okay, and then we go here, and then you see the instruction pointer has now been overridden with our values 41, 42, 43, 44. That is the hexadecimal representation of DCBA. Remember, it is reverse because the Indianness. So that's because of the platform. So we need to do it like that. So when we have it here, then when taken is overwritten into memory, it will be reversed. All right. So now we have taken control of the instruction pointer. So next, what we want to do, because now we have control of instruction pointer, so let's do something. Let's try to jump into a memory location. For example, let's go into, let's reload this. And we can choose, let's choose jump into the entry point. Let's do that. Okay. So we want to jump into this memory location. So remember Indianness. So we need to do it in reverse. So now instead of just going to nowhere, we're gonna move the instruction pointer into the entry point. So let's do that. Just to prove that we have control of the flow of the program. So we do that. Run, run. And let's yeah. Continue execution. The program is running. And then we're gonna run this, crash, paste it here. Okay. Um, and then there you go. But I don't. There is no point into making the exploit for the vanilla type of exploit. So what we're gonna do, we're gonna jump directly into the structured exception handler. Now we have proven that we can control the flow of this, but let me go into here. So how does it work, the structured exception handler? So here is the documentation. I mean, from exploit pack, of course. So as the structured exception handler is basically is a way of controlling exceptions on Windows. So it's not a security mechanism, it's an exception handler. It can be abused, as we say, yes, it can be abused. It can be interpreted as a security mechanism, but it's not a security mechanism. So basically, when an application triggers an overflow, that can be detected by Windows as an exception, right? So it can trigger an exception. So when it triggers an exception, the structure exception handler will try to intervene and control the operation, control the application. So, but it's not only for overflows, right? So as soon as you have an error on the application, then the exception handler, it will point it will jump into the exception handler, and then it will try to handle that exception based on the SEH records. So first, it will jump into the first SEH record, then into the second one, the third, and so on. Right? So it can be abused because the exception handler records the memory addresses that we have here. Let's download the application in order to see it. These memory addresses, they are also in the stack. And if you have a stack-based buffer overflow and you can override the stack, then you can also override the exception handlers. So as you can see, if I have these here, exception handlers, so as soon as you can see that if I trigger, we can run this. I was running. So remember, it's not a security mechanism. So if I run this, take control of A, you see that we're gonna reach memory access violation. So we click on crash, copy this buffer. So it's from the vanilla, is this one. Run the app, GUI preferences, paste the buffer, the malicious extracted buffer there, press OK. We go here and we see here now something different. It says exception access violation. So the exception handler has taken action, and because we haven't overridden the exception handler, now it is taking measures against this exception. No, not against the exploit, it's against the exception. So if we continue this, we see that it's jumping there and is taking control of the exception. Now, of course, the flow is already corrupted because we have overridden stuff, including the instruction pointer, EVX, and some values into the stack, but the exception handler has taken action. So it's not jumping there. That's what we are trying to do, this exception handler exploit, right? So, because we can overwrite the values of the exception handler, yeah, then we can move into those offsets. So remember, we have this, and it says that the exception handler is overridden with pattern at position 1012. So it means that these handlers can be overridden. If you override the values of the handlers, remember, when there is an exception raised in the program, the structure exception handlers will be called, meaning how a buffer overflow happens or something breaks in the application. The structure exception handlers will be called, and how those are being called? By jumping into those. It will jump into the structure exception handlers, but those exception handlers, they live in the stack. So if you override the stack, then you can also override the memory location of those exception handlers. And we're gonna do that now, so you can see it happening. So first thing we're gonna do is to override the exception handlers. If we, I'm gonna open this one. It's basically the same for the vanilla exploit, but let's do it without the exception handlers first. Let's do it choose vanilla with only A's. So it's gonna be this POC. That's this script is gonna choose write 3000 A's in the crash text. But first, what I'm gonna show you is that is going to override this exception handler instead of showing the registers. So let's go into here, restart the program. Oh, first copy 3000 A's, and then go over the breakpoints, GUI preferences, paste here. Okay, and now let's take a look into the exception handlers. And as you can see now, these have been overridden with A's. So 41, 41, 41, 41. That's inside the stack. If I double click on it, that's inside the stack. That was previously the address of the exception handler. And because the buffer overflow has overflowed the stack, we have also overflowed the memory addresses of the exception handler. But the question is, how do we abuse that? Because the problem that we have here now is that if we override the instruction pointer, because this binary is using the SEE, so structure exception handler, if we override the instruction pointer, then the exception handler is overridden. So we cannot control the flow by using the IP. We need to take control of this program using the exception handler. So first, let's restart the program. And let's try to find the memory offsets in the same way that we did with the instruction pointer. All right. So now we know already using the cyclic pattern that what we need to do is override the stack until the position 1012 in order to override the structure exception handler. So this one is 1. And as you see here, I'm adding A's 1012 A's, and then the first value of the first exception handler, the second value of the second exception handler, and then a bunch more A's. And this math, because remember, we are trying to send 3,000 A's. We say that our buffer is 3,000 A's. We can send more or less, but at least this. Why we are sending more? Because then we want to add our code that we want to jump into, right? So first we send 1,000 A's, that will be junk. And this one is going to be the first exception handler, and this one is going to be the second exception handler, and then this is going to be space or padding or space for shellcode that we can use. And this is an arbitrary value that we have chosen to be bigger, to be well, you have to check, because if you overwrite everything on the stack, the application might just crash and not run. And you want to control the application, not corrupt the application. So that's it. So let's run it. And then after we run it, you see that we want to have 1012 A's, and then AB, AB, DD, DD, and then a huge amount of P's that is going to be 3,000, our arbitrary buffer size, minus the chunk, minus 8, and why 8? Because this is 4 bytes and 4 bytes. All right. So we're gonna send that, and this is gonna allow us to take control of the structural exception handler. If we now go there, you see that now you can already see the first chain exception. So the first exception, the first exception handler, is pointing into 41, 41, 41. That's there, and then 42, 42. If we click next, you see that the first exception has been reached from the exception handler into 44, 41, 44, 44. Yeah. So first you get, let's do it. So it's better explained. So first we drop the buffer there. Then the first thing it happens is that you got an exception, because the program is trying to go into 41, 41, 41, 41. So we overflowed the instruction pointer from the stack. So basically the application tried to go back into the flow. So we overflowed the EBP, the back pointer, it was in the stack. The back pointer was moved, the value of that back pointer was moved into the EIP when the function returned. Then the application tried to go to the next operation, and this is the next operation. And then what happened is that it was an invalid position. So because the position of the instruction pointer is 41, 41, 41. So A is not a memory location. So that's why the program has paused and now triggered an exception. If we try to continue the execution from here, the program is using the structure exception handler. And then the program reached the exception handler, but again, stopped the execution because the exception handler also has triggered an exception, because we have also overridden the value of the exception handler. And now the exception handler is triggering an exception itself with the value is exception access violation, because the memory address that this exception handler should be using, as I remember, it was inside NTDLL, but now it's not. Now it's pointing into 44, 44, 44, 44. That is basically this one. 44 is the hexadecimal representation of the capital letter D. If we continue, it will try to go there and then just fail because it cannot go. See? It's trying to go there and it keep on trying to move the flow into that location, but the exception access violation because it is triggered because this position doesn't exist. And if we try to go there, if I click on that memory location, the debugger shows me, hey, the address is not a valid memory location, doesn't exist. So what it means now is we are now having full control of the flow of the program through the exception handler. All right, I'm gonna share here so the code, the Python code, so you can reproduce it on your own machine. And then after you have done that, then we're gonna move into check. Yes, after that, then we're gonna start building the exploit. Gonna give you a few minutes so you can reproduce it, and then we're gonna continue building the exploit. Let me know if you have questions, guys.